Have you ever felt tired after climbing stairs or lifting something heavy? This activity requires effort, and in physics, this effort is called work.
In this video, we will explain work done against gravity, gravitational potential energy, kinetic energy, and power. We will use simple example and video to help you understand this concept.
These ideas help explain many activities in our daily life.
Welcome to the first subtopic, which is work. So, are you guys ready? So now let's start our first mission in work, which is to understand what is actually work. Now, let's focus. So, work is only happen when there is a force that moves an object. So, work is done when an applied force moves an object at a distance. It means that it needs a force and also a distance. From this, we get a formula for the work, which is W equal to F. W is for the work, F for the force, D for the distance. And from this formula we use when we apply on a horizontal surface. And the unit for the work is actually Nm or J. Nm for Newton meter and J for the joule. Let's start our second mission to identify work done. Situation 1. A boy push a horse. So, is there any work done on situation 1? No work done. For situation 1, there is no work done. This is because the boy pushed the horse using a force. The force is applied, but there is no distance due to the horse actually not moving. So, from this situation, we get that there is no work done happening because of no distance. So, let me see the second situation. So, is there any work done for situation 2? Yes, work done is happening. So from situation 2, we got that there are a work done. So why? Let me identify. So first, the cartoon figure pushed the trolley, which is a force. Then the trolley is actually moving upwards, which from point A into point B. So as I can say, there is a distance. So from this situation, we got that there are force and also distance. So work is actually done. Let's calculate work together. So the first question is find work done. So given that the coefficient of friction is equal to 0.4. So let's see the first thing, which is the diagram. So it's given that the force is equal to 11 Newton, the mass for trolley is 8 kg, and the distance is 5 meters. From this diagram, we can actually create a free body diagram. So downward we can see the free body diagram, which there have a force and also normal force, weight downward, and also the friction, which the friction happen when it moves on the rough plane or rough ground. So for A, the work done for weight. As you know, the formula for work done is W equal to Fv. And let us see the free body diagram first, which is weight is downward, and we also know that W is equal to mg, so we change F into mg. So we got that W equal to mg. So from this we can insert the information given, which is M equal to 8 kgs. G is for the acceleration of gravity, which is we use 9.8, and also for the distance we put in 0. So why 0? So we use 0 because the trolley is actually moving horizontally. So there is no moving upward or downward. So that's why the distance is 0. So from this we got that the work done for the weight is actually 0 joule. Let's move into B, which is work done for force. So first, write the formula first, which is W equal to Fp. Then insert the information given, which is F equal to 11 Newton, and the distance is actually 5 meters. So from this, we get that the work done for force is actually 55 joule. Next, C, work done for friction. First, write the formula, which is W equal to Fp. Next, let's see at the free body diagram. So for friction, it's actually opposite direction from the force. So due to this, we need to change the distance into negative 5. This because of the opposite direction. So friction is equal to mu r. So from this, we need to change the equation. W equals to Fd to the W equal to mu RD. So next, let's find R. So R is the same direction with W. So we can change R into mg. So from this, we change the equation one more time until it becomes W equal to mu mgv. So from this, we can insert the information given to the equation, which the mu is 0.4, m is 8, and g is 9.8, and the d is -5. So from this, we got the work done is negative 156.8 joule. Let's see one more video and think, what about this? From the video, you notice that the rock is falling down from the mountain and the cartoon figure trying to stop the rock from falling down. So this is actually involved work done, but this is negative work done. So let's figure out. First, the attempt to stop the rock is actually half a distance, and then it's actually opposite direction. That's why the work done is negative. It's quite similar with the friction, but in this situation, it's actually different due to the mountain have the inclined part, so it has a slope. Now, let's learn second formula, which is W equal to F times cos theta times D. So W for the work, F for the force cos theta if it involves incline or any slope, and D for the distance. So as you see, there is another example like sweeping or mopping, and also try to pull something at inclined plane or something that moving down from inclined plane or moving up to the inclined plane. Now, let's try another example. The question is a block of mass 5 kg is placed on a rock plane inclined at 25 degree to the horizontal. The block reduced from rest sliding 4 meters down the incline. Given that coefficient of friction equal to 0.3, find work done on friction. Next, sketch the diagram. From the diagram, we get the normal force, weight, and also friction that opposite direction from the box that sliding down. So the distance will become -4. Then, start answer the question. First, write the formula, which is W equal to F cos theta D. So from this, we can change F into mu R due to friction equal to mu R. Then we change R into mg. So the new formula is W equal to mu mg cos theta D. So next, insert the information given, which is W equal to 0.3 times 5 times 9.8 times cos 25 degree times -4. From this, we get the answer. Now, you did something about work. Remember, for work to be done or happen, it needs a force and also a distance. The first formula, which is W equal to F, is applied on horizontal surface, while the second formula, which is W equal to F cos theta D, apply on the situation of inclined plane or any slope.
We all know that work is done whenever a force moves an object. But what happens when the object moves upward against gravity? Come on, let's see a simple example first.
Daryl, come back, man! Where are you going?
I can't go anymore.
Look at the bears climbing the stairs. They are chasing someone, but let's focus only on the upward movement. Notice that as they goes up, they apply a force opposite to gravity. So, every time the bears climb upward, they are doing something. In physics, it is called work done against gravity. Anytime you lift an object, you do work against gravity. Work done against gravity occurs whenever a force is applied to move an object upward, opposite to the pull of gravity. Even everyday actions like climbing a ladder, going up in an elevator, or lifting a bucket from a well involve this type of work. Now, let's look at another situation where work is done against gravity. Watch how the object is lifted upward. In this situation, the blue cat, Tom, lifts the small weight using one hand. It moves upward against gravity, so work is done. Since the weight is small, less work is required. Let's move on to the next situation. Meanwhile, for this situation, Tom tries to lift a heavier weight. It's harder and he eventually falls. This shows that heavier objects require more work to lift the same height. Alright, now let's try a quick question. Based on both videos that you have watched before, which situation involves more work done against gravity? Is it situation A, small weight, or situation B, big weight? Alright, time's up! Yes, the answer is situation B, big weight. Heavier object equals to more work. So, what actually affects work done against gravity? Actually, there are two main factors that affect work done against gravity, which are first, mass of the object, as well as height lifted. Heavier objects need more work, and lifting the objects to a higher position also increases work done. For your information, we use the same formula for work that you already know, which is W equals to Fd. In work against gravity, force is written in the form of mg, while h is the vertical distance. Therefore, W equals to mgh, where m is the mass of the object, g is acceleration due to gravity, which value 9.8 meter per second, and h is the vertical height. Now, let us try this simple question. A woman lifts a book from a box on the floor and places it onto a table that is 0.6 meter high. If the book has a mass of 1.5 kilogram, how much work is done against gravity? From this question, given that the mass of the book m is 1.5 kilogram, acceleration due to gravity g is 9.8 meter per second, and height lifted h is 0.6 meter. Now, you can substitute the value given into the formula W equals to mgh. W equals to 1.5 times 9.8 times 0.6. And the final answer is 8.82 joule, or you can write it in Newton meter. Alright, we're focused on work done while moving objects upward. Next, we'll discuss what happens to these objects at the top, connecting to gravitational potential energy.
Hi everyone! Now, let's take a deep breath for a moment. So far, we have learned about work and work done against the gravity. Now, let's move on to another important subtopic, which is the energy. In physics, energy exists in many different forms. For this topic, we will focus on two main types of energy, which is the gravitational potential energy and kinetic energy. For my part, I will start by explaining gravitational potential energy first. Later, my teammate will continue with the kinetic energy. But before we go deeper into the definition, let's first take a look at some short video example that I give. The first example shows a person standing on top of a slide. The second example is diver standing on a diving board. And the third example is show a hiker at the top of a mountain. The question is, why does heat matter in physics? Why does simply being at the higher position make such a big difference? Have you guys ever wondered how an object can have energy even when it's not moving? Where does that energy come from if there is no motion involved? This type of energy is called gravitational potential energy, or we call it as the GPE. Gravitational potential energy is the energy stored in an object due to its vertical position or height. In simple terms, actually, gravitational potential energy is energy stored because of height. The higher the object is, the more gravitational potential energy it has. Okay, now let's stop here for a moment. Instead of just looking at the formula I give, let's see how it actually works using an example. Now let's look at our first example. Ahmad placed a 2 kilogram book on a shelf that is 3 meters above the ground. The question is, what is the gravitational potential energy of the book? First, let's visualize the situation. Imagine Ahmad placing the book on top of the shelf. As we all know, the mass of the book is 2 kilograms and the height of the shelf is 3 meters. Okay, now let's use the formula for gravitational potential energy. GPE equals to M multiplied by G multiplied by H. Here, M is the mass of the object and the unit must be in kilograms. G is the gravitational acceleration, which is 9.8 meters per second squared. And lastly, H is the height above the ground and the unit must be in meters. Our final answer must be written in joules, or we simply can write it as J. So, in this example, the mass is 2 kilograms and the height is 3 meters. By using the formula of GPE equals to mgh, we substitute the value. So, GPE equals to 2 times 9.8 times 3. This gives us the final answer is 58.8 joules. That is the gravitational potential energy of the book. Now, let's take a look at another example. A climber with a mass of 80 kilograms scales a mountain that is 1.5 kilometers high. We are asked to find her gain in the gravitational potential energy. Let's imagine this climber and we will call her Siti. Siti is climbing up to the mountain. Siti has arrived at the top of the mountain. Her mass is 80 kilograms and the height of the mountain is 1.5 kilometers. By using the formula, the mass is 80 kilograms. G is the gravitational acceleration, which is 9.8 meters per second squared. However, the height is given in kilometers. Since the height is the formula must be in the meters, we need to convert 1.5 kilometers into meters first. So 1.5 kilometer multiplied by 1000 give us 1500 meters. Okay, now we substitute all the values into the formula. GPE equals to 80 times 9.8 times 1500. This gives a gravitational potential energy of 1176,000 joules. To summarize, gravitational potential energy depends on the mass of the object and the height of the ground. Even when an object is not moving, energy is already stored because of its position. As you can see, when the object starts moving, this stored gravitational potential energy is converted into the kinetic energy. Next, my teammate will explain kinetic energy in more detail. Bye-bye.
Before I explain how gravitational potential energy in the ball is converted into the kinetic energy when it falls, let's first take a look at the theory behind work and energy because any moving object is need both of it to causing the movement. Work is the action that causes movement of an object, as work transfer energy into the object or from the object. On the other hand, energy refers to the ability to do work, or in simple way, we see that energy is the result of the work. From this definition, we can see the clear connection between work and energy. This leads us to work energy theorem. The work energy theorem states that when work is done on the object, its kinetic energy will change by same amount. In other words, work done on an object is equal to the final kinetic energy of the object minus its initial kinetic energy. But what is kinetic energy? Kinetic energy is the energy possessed by the object due to its motion. It is given by this form. So, that's why we get this form as our final work energy theorem formula as we substitute kinetic energy formula into it. Using this theorem, now we can explain how different types of work affect the motion of an object. Let's take a look on effect of positive and negative work. Positive work is done on an object such as pushing static trolley forward. We can see the trolley moving faster than its initial state. This is because kinetic energy of the trolley is increasing. However, for negative work, when the trolley moving forward, at the same time there's a friction acting on it, which eventually the trolley will slow down and stop. The trolley slow down because the kinetic energy decreasing. But how does kinetic energy decreasing or increasing? According to the principle of conservation of energy, the total energy in the closed system remains constant because energy cannot be created or destroyed. It only can be transferred or transformed from one form to another. So let's see how this principle is applied in the falling ball situation. The ball just about to fall and still at rest, no work has been done on it. Therefore, its kinetic energy is zero, while its gravitational potential energy is maximum. Because it is at the greatest height, the ball is falling, a gravitational force acts on it and does positive work. As the height of the ball above the ground is decreased, its gravitational potential energy also decreases. The work by the gravity causes the gravitational potential energy to convert into kinetic energy. So, kinetic energy increases. Before hitting the ground, the ball has maximum kinetic energy and minimum gravitational potential energy because almost of its gravitational potential energy has been converted into kinetic energy. Since we have covered theoretical explanation on work energy theorem and the principle of conservation of energy, let us now take a look at some examples. Exercise 1. A ball of mass 2 kg is initially at rest. A force does 20 joules of work on it. Find the final kinetic energy of the ball. To solve this question, we need to use the work energy theorem formula, which is work done equal to final kinetic energy minus its initial kinetic energy. From the question, we can get value of work done, mass of object, and its initial speed. Those values, we need to substitute it into the formula. Therefore, we get final kinetic energy is equal to 20 joules. Exercise 2. A 2 kg object is at rest at a height of 3 meters. A. What form of energy does the object have? The answer is gravitational potential energy because the object has height. B. What happened to the energy when the object falls? The answer is the gravitational potential energy is converted into the kinetic energy. In summary, we already learned what is kinetic energy, the work energy theorem, and the principle of conservation of energy. However, the rate at which energy is transferred has not been discussed yet, but this topic will be covered next.
We have discussed work and energy. Power is related to this concept because it measures how quickly work is done. Now, I will explain power. Superheroes like Spider-Man, Batman, and Superman have amazing powers that they use to save the world. We all admire them and wish we could have superpowers too. Who wouldn't want to be able to fly, climb walls, or have super strength? But in physics, power has a very different meaning. It is not about super strength or flying. Power is the rate of doing work. So, the idea is just like this. Imagine there are two people that have the same amount of work, but one of them managed to finish his work faster than the other one. So, the one who finished the work faster have the higher power output. The basic formula of power is work done over time. Work can be represented as force multiplied by distance. We can rearrange it into force multiplied by distance over time. Distance over time is velocity. So, power is equal to force multiplied by velocity. The unit of power is watt. So, what is watt? Watt is joule per second. Joule is the unit of work and second is the unit of time. So, basically, 1 watt equal to 1 joule per second. Now, suppose that this light bulb is a 40 watt light bulb. It means this light bulb converts 40 joule of energy into light every second. Okay, now we have two light bulbs, light bulb A and light bulb B. Light bulb A use 1200 joule in 20 seconds and light bulb B use 1600 joule in 40 seconds. By applying this formula, it is known that light bulb A has 60 watt of power and light bulb B has 40 watt of power. So, light bulb A has a higher power than light bulb B. Light bulb A is brighter than light bulb B. Now, let's solve this problem together. We are asked to calculate the average power of a crane. First, let's identify the given information. The mass is 200 kilograms, the height is 40 meters, and the time taken is 106 seconds. To calculate power, we need to find the work done first. Since the object is lifted vertically upwards, the work done is given by the formula mgh. So, work done equals to 200 multiplied by 9.8 multiplied by 40. This gives us a value of 78,400 joules. Next, we calculate the average power using the formula. Power equals to work done divided by time taken. Power equals to 78,400 divided by 106. Therefore, the average power of the crane is approximately 740 watts. That's all for my part. Thank you.
In this video, we learned about work, energy, and power. We explored work done against gravity, gravitational potential energy, and kinetic energy.
This concept helps us understand everyday actions like lifting the objects and climbing the stairs. Physics explains how the world around us working. We hope that you learn something from our video.
Thank you for watching!